Esta
this second
conferencia
webinar
comenzará a grabarse.
that we are now organizing in the Spanish Association of Professional Geologists. We are going to have the profit and also the opportunity to have some presentations. So Audrey is going to perform the one today, and then Gonzalo Ricebrian on the 21st. So after that, we're going to have a short course on geothermal process and techniques that will be given by Colegio Oficial de Geólogos from our institution and also from Geoxilia. So thank you very much, Audrey. Merci beaucoup. The floor is yours. You may start when you want. Thank you much.
Thank you, Carlos. Thank you to ICOR to invite us for the second part of the geothermal systems cycle of conference. And this presentation, I will focus on the case study of hydrothermal system, which was actually the subject of my PhD. Oh, I can't go to, yes, okay, it works like this. So just before, for the people which weren't there at the last session, I will quickly present Geoxilia. So Geoxilia is a company that is present worldwide and can provide a personalized solution for training, mentoring, and consulting. And Geoxilia has experiences in several domains, for example, database, sedimentology, geophysics, structural, petrophysics, EOR, geothermal reservoir, project management, gestion, drilling, and geomodel. Geoxilia supports the oil and gas industry in the way of the energetic transition, but is also involved in sectors such as ensure the safety of the subsurface products, such as radioactive waste. And so we are very attentive to innovation. So if you need us, please contact us. This presentation will be in 3 parts. In the first part, I will give a definition of hydrothermal system, an idea of how we can use the hydrothermal fluids, and a reminder of the last presentation, which was about geothermal system. In the second part, we are going to see the case study of the TET hydrothermal systems, which is located in Eastern Pyrenees. And in the third part, I will give some example of hydrothermal system in Spain. So the hydrothermalism or hydrothermal systems, I will give a definition for this presentation, which is that geothermal circulation of hot fluid that manifest at the surface at hot spring. So these hot springs are known in the Roman age. On the top left, you have a pictures of the Dores hot springs in Sardinia. And this bathroom actually is dated from the Roman age. So you can enjoy hydrothermal fluid for the touristic activity. And actually it's important because they are often located in mountainous area, where there is no such economical activity. These fluids have a medical application because of their composition or because of their temperature. And finally, because we have the manifestation of the surface of hot spring, maybe this hot spring could indicate us a geothermal potential of the area. So just a reminder about how works the geothermal systems and what are the factors that control the geothermal circulations. So in a hydrothermal system, we have a hot spring at the surface, and so we need infiltration inside the crust of meteoric or marine water and the circulation of this fluid inside the crust. So the circulation will depend on the permeability of the crust, which is related to the permeability of the lithology, the presence of fault and fractures, and the in situ stress. To heat this fluid inside the reservoir, we need heat sources, which is related to the heat production of the rocks themselves, to the heat flow, which is related to the geological context or the presence of abnormal heat anomalies such as plutonism or volcanism. And we also depend on the thermic regime, which is actually related to the mode of heat transfer inside the crust. So there is free heat transfer mode inside the crust, the conduction, with us the transfer of fluid, the free convection, which is related to the transfer of fluids because buoyancy forces, and which mean the difference of density related to the temperature of the fluids. And finally, by advection or forced convection, which is the transfer of fluids related to a pressure gradient, usually the topographic gradient. So just keep in mind 3 important points for this presentation about the permeability. I said that permeability highly depends on the presence of faults, because faults are actually composed of a core zone, which is formed by crushed rocks, cataclastic rocks, which is usually considered as being impermeable, and by 2 domain zones that are area where the rock is highly fracturated, and it's usually considered as a very permeable area. Also remind that the rock produces their own heat, and that granite and gneiss actually have the most important heat production compared to the other rocks. And finally, also remind that inside the same hydrothermal or geothermal systems, we are able to find further heat transfer mode. In this example of the Dixie Valley in Nevada, you have free convection inside the basement and the basin and the faults, and advection of fluids because of the topography adjacent to the main fault. So we will see this context, but applicate to the TED hydrothermal systems. So it's a very nice region, and yes, you can enjoy actually hot spring inside the nature. Here you have a picture of electrical investigations that we have made at the vicinity of the hot spring, but the result weren't so good, so I don't will show you this part. So just to locate the study area, which is located inside the Pyrenean Ranch. So Pyrenees are a range at the boundary between France to the north and Spain to the south. It's a range that has formed during the Eocene because of the collision of the European plate with the Iberic plate. This range is formed by a central part called the Axial Zone that is composed of basement rocks, and this zone is surrounded by Mesozoic rocks and by a tertiary basin inside the forelands. So on the image on the top, you see the small rounds that are the hot spring everywhere along the Pyrenees, and with high temperature that could reach 75 degrees. And we see that there is 2 main clusters located inside the axial zone on the west, and another clusters with high temperature hot spring in the east of the axial zone. So if we focus on this cluster, is the picture just below. Yes, we see that there is hot spring. The hot spring are mainly concentrate along a main fault, which is the TED fault. The TED fault actually is a very long fault, crustal fault, that across the axial zone. And this fault is part of a fault northeast-southwest fault network, such as the Tech fault, which also localize hot spring. And this fault formed during the opening of the Gulf of Lion during the Oligocene extensional episodes that have allowed the opening of the Mediterranean Sea. This fault is a normal fault that records an offset of more than 2,000 meters inside its hanging walls that have created the relief of the Canigou and the Carrancha. We also see another fault network composed of northwest, southeast faults that across the study area, and in Catalonia they are related to El Empordà range and the transverse range. We also observe a small fault, the Capsa fault, which have a north-south orientation and which is actually not very well explained because there is not other fault with such orientations. So we have many hot springs along these faults that across the basement, which is here composed of gray metasediments, in red of granite, and in orange of gneiss from the Hercynian period. So if we have a look on the topography, here on red, you recognize the Tet fault, and in its footwall, you see the topography associated with the 2,000 meter offset that correspond to 3 main ranges. On the east, the Canigou ranges, in the central part, the Carranza ranges, and on the west, the Piuxmal that reach an altitude of 2,000 meters and 900 meters, 2,900 meters. So if we have a look on the hot spring, we observe 4 main clusters along the Tet fault. And if we look on the sketch on the bottom right, from the west to the east, we can separate these 4 clusters individually. So we have the Leo clusters, a single hot spring with a temperature of 29 degrees. Eastern, we have the Saint Thomas and Prats clusters with hot springs that could reach 60 degrees. Eastern, we have the Thuès and Canaveil hot spring clusters that could reach 73 degrees. And eastern, at the bottom of the Canigou, we have the Vernet hot spring clusters that could reach 75 degrees. So the question of my PhD was which are the factors that actually control the distribution of this hot spring along the Tet faults, and the question was to understand how works these hydrothermal systems. So usually when we study geothermal systems, it's better to have the more information we are able to find. So in making remote sensing and fieldwork, we are able to map the lithology and fault and fracture at the surface of the systems and the location of hot spring. But we have also access to different information in subsurface, such as geophysical survey and geochemistry and well data. And all of this data allow to make numerical modeling of the geothermal fluid circulation. But actually, for the study of the Tet fault systems, we are located in an area where there is no issue for geology, such as oil and gas exploration or mining. And so there is no well data and practically no geophysical deep investigation. So we make remote sensing and field data to access to surface data, and also geochemistry to access to some subsurface information. Surface data allow to build a 3D geological models, which were realized on the GeoModeler. And with this geometry, we feed heat and fluid transfer numerical models on COMSOL multiphysics. And the comparison of the results of this model with the data, and I will say why this is very important to come back to data, give us access to the processes and to the data that are not available with the surface data. So because topography is very important for geothermal systems, we start to understand the relation between topography and the hot spring systems with remote sensing. So on this graphic, on the bottom right, you have here the distance along the TED fault from the west on the left to the east on the right. So that corresponds to a line along the TED fault here from the west to the east. And so we are able to find the hot spring clusters and to report the spring temperature on the right of the graphic. So we find the 4 main clusters with the low clusters, the single and not very warm hot spring. And in the central part, we have the 2S cluster with the warmest temperatures and the high number of hot springs. And so we have a pyramidal organization of the hydrothermal systems. We have made an evaluation of the topography inside the footwall. So on the map on the top right, you have a map of the topography, and be careful because the north is at the bottom of the graphic. An evaluation of the topography inside the TED footwall, which correspond to the elevation of the scarp associated to the TED fault. So the difference between the maximum of altitude of the relief with the altitude of the fault outcrop. So this is reported into these green lines here. And so we recognize the Pushmal scarp, which is actually a small scarp. The Pushmal is 2,900 meter height, but the Sardinia Basin, which is located here, is actually very high. So the scarp, it's not so important, and is related to this single and not very warm hot spring. The other spring are related to a more important scarp. And so here the Canigou have a very important scarp, but we have to consider the presence of the P fault, which has also recorded a part of the offset of the Canigou. So there is a relation between the topography and the organization of the hot spring systems. And if we compare with geochemistry, it will give us even more information. So geochemistry of the hydrothermal fluids give us some information about the age of the meteoric water that have fed this hot spring. So the age of the meteoric water are between 7,000 and 10,000 years old. So it's very old water. And geochemistry with the isotope of oxygen also give us the infiltration altitude of these fluids. And so reported on the same graphic, we find again the organization, pyramidal organization of the hydrothermal systems that is also related to the infiltration altitude of the meteoric fluids. And we see that this infiltration is more or less 2,000 meters, and so correspond to this yellow area in the picture on the top left. So I don't understand why it's not appearing well. It's strange. But okay, so remote sensing also allow us, it's okay, also allow us to map lineament at the surface of the AM or to spot pictures. And lineament actually correspond to small fault or to large fractures that appear and modify the surface of the study area. So this is the free picture on the left that corresponds to this lineament map, and we classify it according to the main fault orientation. So in red, you have the orientations that correspond to northeast, southwest lineaments that correspond to the TED fault and to the P fault. In green, you have the northeast, southeast faults that correspond, for example, to the Nuria fault or the Walter fault. And in blue, you have the north-south lineaments that correspond to the Capsia fault. And so that allows us to have a map of the small fault and fractures at the surface of the study area. This leads us to a map of the lineament density. So in white, you have no lineaments, and in black, you have the maximum of density of the lineaments. In blue, you can observe the impluvium area that corresponds to meteoric fluid infiltration area, 2,000 meters. That's well revealed by the geochemistry. And in red, here you have the recent sediments filling of Neogen basin, quaternary glacial deposit, or alluvions. So we see that we observe high lineament density at the vicinity of some hot spring, for example, here in Suez, or for example, at Lio. But we also observe this high lineament density inside the impluvium area at the vicinity of the northeast southeast faults. And what's important in mapping these networks of faults and fractures, it's because fault and fracture actually may enhance the permeability of the Earth's surface, and so allow fluids to circulate more easily on the impluvium area or at the vicinity of the hot spring. So that method allows us to access to the fracturation at the surface of the study area. If you are lucky and if we have borehole in the study area, we can have more information about fracturation inside the crust. And so for this, I invite you to assist to the conference of Gonzalo, and that will be in the coming week, the Wednesday 21st at the same hours and today, about borehole image analysis and overview. But it wasn't the case for my study area. So important fieldworks allow us to have a precise map of the lithology, the fault and fracture network, and the position of the hot spring inside the study area. So we recognize the 4 clusters of hot spring, and we see that they are aligned and at the vicinity of the TET fault, and practically all the hot springs are located inside the TET fault footwall. There is the exception of Canavay, where 3 hot springs are located in the hanging wall. We also observe on the field that the hot springs are always emerging inside crystalline rocks, so granite or gneiss, and at the vicinity of a contact between these crystalline rocks and metasediments. We also observe that the hot springs are located at the vicinity of fault intersection, northeast-southeast fault with the main TED faults, such as in Lio, or here at Prat. And yes, please remind about the Prat fault, which will be very important for the coming session. There is one exception of Vernay-les-Bains, which is not directly at the vicinity of the TED fault, but southern, and is actually located on Nersinian mylonite, the CMNC, that's put into contact crystalline rocks in its footwall with metasediments inside its hanging wall. So on the field, because it's the nice part of studying geothermal systems, the hot spring of Lio, so the western hot spring, look at this picture. So you have the Lio spa here, which is very nice, but actually the hot spring is located in these small houses. So we are lucky here to have a view on the parking, this flat area of a TED fault, where we can see the TED fault easily. So it's look like this. The hot spring is located inside fractured gneiss of the TED fault damage zone, so very permeable rocks. And so yes, you can see the fractured gneiss inside this picture surrounded by green. The TED fault here is mainly composed of cataclysmic fault rocks, so very crushed rocks that you can see on the picture surrounded by red here. So you see it's very crushed, and it doesn't look very permeable. And here the TED fault put into contact gneiss in its footwall, where is located the hot spring, with metasediments in the hanging wall. And northern, we find the Sardinian basin. So if we go eastern at Thues cluster, it's a place where there is the warmest temperature with many hot springs. Here, most of the hot springs are located in the footwall, but we find 3 hot springs which are located in the hanging wall in Canaveil. And actually, here, the TED fault put into contact crystalline rocks in its footwall and in its hanging wall. So maybe there is a relation with the location of the Canaveil hot spring inside the hanging wall. So here we observe the fractured damage zone, very fractured gneiss here. And the TED fault is composed of multi-core, composed of cataclysmic fault rocks. You have here, surrounded by red, a thin section that represents the cataclysmic fault rocks, with here the breccia, cataclysmic breccia. Here we have cataclysite, and here we observe also ultra cataclysite, so high quantity of matrix and no more fragments. We also observe siliceous sinter at the vicinity of the border of the core zone. And finally, eastern at the bottom of the Canigou, if we have a look on the cross-section of the Vernay hot spring, we see that these hot springs are located on the ductile mylonites from the Hercynian age, and not related directly to the TED fault, but at the contact between metasediments in the hanging wall of the mylonites and crystalline rocks inside the footwall of this mylonite. And if we have a look on this mylonite on the field, we are very surprised to observe some cavities aligned with the foliations. And so that's strange, because we are not in carbonate rocks. It's not so easy to make some such dissolution cavities in crystalline rocks. So maybe that could explain the presence of hot spring here. all of these informations allow us to feed 3D geological models on the GeoModeler. And so here you have the representation of 3 main faults: the TET fault in red, the P fault in orange, and the Pratt fault in green. And so for the coming simulation, we will consider 2 models. A first model with a single fault, the TET fault, and a multi-fault model, including these 3 faults. This geometry has fed a heat and fluid model composed of the Darcy law and the heat equation. For the topography, we use a DAM, and we have tested further type of range of permeability for the basement and for the faults. On the top left, you have the result of this simulation that show the flow lines that circulate inside the models. So this is a view from the east to the Tet Valley. So here you recognize the Canigou. We continue and we are here in the Carrancha, and we continue and we are here on the Pushmal. Here is the Tet Fault. We are in the signal fault model for the simulation. So what we observe is that meteoric fluid infiltrate on the relief, and because of the topographic gradients, they are driven down inside the model, inside the basement, and will be heated at 3 kilometers depth. And after driving in the direction of the valley and will be caught by the Tet Fault, and so are able to upwell because the Tet Fault here is more permeable compared to the basement, because we consider the Tet Fault damage zone that is a high permeability area. So if we have a look on the distribution of warm fluid along the Tet Fault, so it's the picture at the bottom left, we see that we have an alternation of positive thermal anomaly with upwelling of warm fluids that actually correspond to the hot spring we observe in the nature at Vernet, at Thues, and at Lio. Small exception of Saint Thomas and Pratt, and we'll come back to this. But we also observe that we have alternation of this positive thermal anomaly with negative thermal anomalies that actually correspond to area infiltration where cold fluids are driven from the surface along the Tet Fault and will be heated here and will have to contribute to the surrounding hot spring. So if we make a cross section to this infiltration area, is the A cross section, we see that there is a depletion, a down depletion of the hydrotherm at the vicinity of the Tet Fault here. And if we make a cross section, the cross section B in positive thermal anomaly area, we see that there is an upwelling of hydrotherm at the vicinity of the Tet Fault in Thues. And so this is the target area if we want to find a geothermal system. As I've said, we have a problem with Prats and Saint Thomas. Here on the top is a map of the single fault model, only considering the Tet Fault. So we were able to reproduce the Thues hot spring thermal anomaly, but here we are not able to reproduce the Prats Balaguer and Saint Thomas hot spring. So we make a multi-fault simulation, which is on the sketch on the bottom left. And what we see, we had the Prats fault and the P fault, and what we see is that fluids actually infiltrate on the relief and follow the Pratt's fault to get down, be heated, and actually contribute to the Pratt's fault, the Pratt's and St. Thomas hot springs at the intersection between the Pratt's fault and the Tet fault. Actually, if you remember of the last presentation, we said that intersection area between two faults are area where there is a damage zone intersection. So it's very permeable area. And if we look on a map of this thermal anomaly at the surface, in the multifold model, we are able to reproduce the hydrothermal anomaly at Prats-Balaguer and St. Thomas. So this says to us that these systems are highly complex because of the topography that's actually control a large part of the hydrothermal circulation, and because there is a complex fault networks that could importance for the fluid transfer inside the crust. Okay, here we come back to a graphic depending on the distance along the Tet fault. So you have here the Tet fault from the west, which is located on the left of the graphic, and the east of the Tet fault is correspond to the right of the graphic. And we report the temperature inside the simulation, the temperature reached at depth inside the simulation on this graphic. So we observe the same pyramidal organization of the hydrothermal systems. And inside the simulation, so it's the blue, we see that the fluids at 2S could have reached a temperature of 160 degrees. And so if we are looking for exploration of geothermal systems and we want to target this temperature, we said, okay, that's super nice. Numerical models say that at 2S, if we drill, we are able to find this temperature. Actually, if we make some geothermometer on the hydrothermal fluids, we see that, and it's the part in gray, where we observe the same organization, that's okay. But we see that we weren't able to reach more than 130 degrees at the 2S hot spring. So my message for this is that numerical simulation could be very sexy, but it's actually just a representation of the reality, and we need to make methods feedback all the times and to come back to the data. Plus, the systems that this alternation of positive thermal anomalies that correspond to hot spring and negative thermal anomalies that actually correspond to infiltration area, there is only few kilometers between these two zones. So we need to very well understand the complexity of this in order to make geothermal exploration in this area. So this is a sketch that resume the Tet hydrothermal systems. So you recognize Tet fault, the Lieu, St. Thomas, Prats-Balaguer, Canaveil, 2S, and Vernet hot spring. We have systems of three main ranges, Puigmal, Carancha, and Canigou, that are related to the offset along the Tet fault. And so fluids have been infiltrated at an altitude of 2,000 meters on this relief. Because of the topographic gradients, they will reach high depths where they are going to be heated, especially in the central part, because the topographic gradient is more important. And because of the presence of the damage zone, very permeable of the Tet fault, they are going to reach the surface and make hot springs. It's especially the case at Saint-Thomas-les-Bains and Prats-Balaguer, where the intersection between the Prats faults, which have its home damage zone, will provide a very permeable area at the intersection zone. And finally, I just remind the exception of Vernet, which is located on mylonites, whole mylonites, and the fluids are going to use this old fault, which put into contact metasediments less permeable with crystalline rocks more permeable. So if we have a look on hydrothermal system in Spain, and I will be very quick. On the left, you have a map of the mineral waters and hot spring in Spain. So there is this hot spring practically everywhere inside Spain, but we are able to make some cluster of this hot spring. The cluster are here in red on the geological map. And so if you remind of the presentation of the last week, we have seen that here in Galicia, where there is the most important cluster of hot spring, we have observed a very high temperature anomaly in this area that is actually related to Hercynian massif in Galicia that contain high volume of crystalline rocks, gneiss and granite. And we also observe this cluster of hot spring inside the Catalan coastal range, Cordillera, and inside the Pays Basque, the Basque country in English. And in this area, we actually observe many faults and reliefs that are related to these faults. These clusters actually correspond to a geothermal area in Spain. We have seen this map last week that actually correspond to median high temperature geothermal potential. So hot spring give us information about geothermal potential in a study area. We are able to differentiate three kind of hydrothermal fluids feature depending on the chemistry mainly. So the hot spring in the fractured granite, which are sodium bicarbonate type with the presence of sulfide in Galicia, Salamanca, Pyrenean and Catalonia. The hot spring in the limestone in the porous karstic type in Iberian, Betic and Cantabrian Pyrenean Range. And finally, the hot springs that are located inside the Paleozoic rocks from the Betic Range. I give you two examples of hot spring in Spain. On the left, you have the example of Panticosa, where there is the infiltration of meteoric fluid on the Panticosa granite that could reach high depths and reach temperature of 90 degrees, and use faults to join the surface, where the warmest hot spring have a temperature of 47 degrees. And so what's interesting here, we have a lake and there is a declination of temperatures and geochemistry feature of the different hot springs that actually correspond to a pollution of the hydrothermal fluids by meteoric fluid from the highest temperature to the lake composition. On the right, we have the example of the Ardenillo thermal spring, which have a temperature of 70 degrees. Here, the hydrothermal fluids circulate along a carbonate evaporitic aquifers below an impermeable formation, and use thrust inside the Pyrenean foreland to reach the surface. So the temperature at depth is estimated to 87 degrees. So as a conclusion, hot springs are the manifestation of a deep positive thermal anomaly at the surface that could give us an idea of the geothermal potential of the area. But hydrothermal systems are located in very specific topographic and geological settings. And so because this is very complex, remains to be studied. We have seen here that with a combination of surface data, remote sensing, geology, geochemistry, and numerical modeling, we access to an inexpensive exploration methods that give us a first overview of the systems before to drill where there is no deep data. But I insist because we have to be careful to make a constant feedback between the different methods. And so that's kind of study that we can propose in GeoAuxilia. So if you are interested, please contact us for this. Thank you again to Carlos and to Icor to invite us, and gracias por su atención. We have time for questions now, but if we don't have time for all the questions, please write to me an email. Thank you very much.
Thank you very much, Adri, for your kind presentation, which has been quite fruitful. And I think if the audience, some of them would like to ask a question, we are ready to pass you the questions. Si alguien quiere preguntar, le pasamos la pregunta a Audrey.
Well, I'm Gonzalo. Thank you very much, Audrey, for your presentation. I think the next week I will try to make the same level that you made today.
I'm sure you will do it.
Presentation. So now people ask to Audrey. She's the expert of geothermal studies. Go ahead.
Please.
Not many questions today.
How many questions?
Is everything clear? Okay, well then, let me tell you that in the near future, we're going to have a short course in geothermal exploration that will be given by GeoAuxilia in cooperation with the ICOG, the Spanish Association of Professional Geologists. I think it would be quite profitable, and also we got to think that in Spain we have the opportunity to provide hot water, heating and cooling for the buildings, and a lot of funding has been provided by the European community. So then we may have a chance, as I said, is the niche in which the market of the geologist may develop his profession, and it's also a scientific challenge. So I hope this course will maybe then helpful to all the geologists that we are here in Spain to acquire the knowledge enough to participate in those projects. Any questions?
Apparently,
right, here you have one.
About helium.
Yeah, right. Is there any helium? From Daniel Alonso? Thank you very much for your question. Daniel says, is there any helium isotopic data on these and other hot springs in Spain?
Actually, I don't have the answer, but I can have a look. I have many papers about geochemistry of hydrothermal hot spring in Spain. So I will check and I come back to you.
Yeah. Angel, thank you very much. Angel is asking, hello, I do have a question. I'm curious to know the age or the duration of these hot springs.
The age for this hot spring, so it's based on 14 carbon, but we have to be careful about this. But the age given for this hot spring are between 7,000 to 10,000 years. So it's
Right.
very hot. It's old hot springs. It's old meteoric water. The age of the hydrothermal systems, if it is the question, yes, we have seen that this system is related to the Tet fault and to the relief inside the Tet footwall. So we can suppose that the age of the hydrothermal system is actually the age of this mountain range that are formed during the Oligocene to the Miocene.
All right. We have another from Jesus Sotomayor. Thank you, Jesus. Can you give us more info on the measurements made for the fracture density at the elevated surfaces around the Tet fault?
For the fractures density, actually it's a big fieldworks investigation. We'll come back to the pictures if it okay. So during 3 months with 2 students, we make fieldworks over the walls to the area, and we take measurements of fractures at more than 300 spots, and we measure fracture with actually an application of Midland Valley on the iPhone. So it gives us so this for this pictures we only made handmade. We have mapped all these lineaments by hand on QGIS, but we also have made fracture measurements on the fields, and we have a big quantity of data. If you are interested, it's actually an article that I'm writing, and which is accepted, and we will be published, I hope, soon.
Yeah, we have a few more questions. That one is from Maria Barrio Lopez. Thank you, Maria. She says, hello, Audrey. Thank you for your presentation. I would like to know how flow lines are modeled. Which kind of data do you use?
Okay, for the models, we use COMSOL multiphysics, which is a model that's compile the Darcy law with the heating equation. And so we put mixed thermal boundary condition on the topography, and we allow fluid, and we put a permeability inside the basement. And so we let the fluids circulate because of the pressure of the atmosphere on the topography. So we don't use actually data for this except the topography, and we let the simulation works and calculate the flow lines.
Okay, we have another one here from Daniel Diana Allard. Thank you, Diana. She says, have you worked in Latin American projects or have any insights of what methodologies could be more successful for systems in the Americas? Thank you.
I didn't work on a Latin American project, but I know that there is many hot springs that could be related to the volcanic activity, but there is also interesting hot spring where there is no volcanic or low activity volcanic activities that are related on. And I know that there is all the bibliography about a topographic relation with this hot spring, which is currently published. So I could send you the references. And yeah, the methodology that we can use depends on the data that could be available. And in area where there are such deep data, for example, mine or wells, I think that we could approach a first exploration of the systems with this kind of methods, different methods, and make a simulation of hand with the data we are able to find. So please write an email to me and we can discuss more of the methodology we can adopt for these systems.
Yeah, here we have another one from Daniel Alonso. Thank you, Daniel. And he is asking, is there any mineralogical evidence of fossil hydrothermal circulation systems in the Pyrenees that might provide analogues of the possible maximum temperature and chemistry of the currently active hot springs?
I'm super happy you asked this question, because actually I didn't speak about what point. On the simulation, you see here that we are supposed to find a thermal anomaly between Thues and Saint-Thomas here. Actually, in the reality, there is absolutely no hot spring in this area that could be observed. But if you make a walk inside the Carranza Canyon, which is just here, we find actually fractures that are filled with silicate and carbonate. And so there is actually currently a study at the University of Montpellier. It's the works of Gaëtan Milesi, and I have a slide for this. Gaëtan Milesi is using thermochronometry on apatite to try to reveal the presence of a thermal anomaly. So usually thermochronology is used to reveal the offset along a fault. But what Gaëtan is showing is that at the vicinity of a fault where there is hydrothermal circulation, we observe a variation of the age of the thermochronology. And so, yes, in using this methodology for just access to the fault offset, we have to be very careful at the vicinity of this hydrothermal zone. And maybe we could use this methodology to access to paleo systems where no hot springs are observed currently, but where there is problem in making thermochronology.
All right, then we have in here another one from Jesus Sotomayor. Thank you, Jesus. He's asking, if the water geochemistry shows ages from 7,000 years or more, it means the trapped water may be small, and the replacement water may be small. In your experience, does this limit the potential of large heating potential, or it means that more studies are required?
That's actually the problem of the geothermal system inside crystalline rocks. Actually, aquifer inside crystalline rocks, inside basement, are not well known because it's not a proper aquifer as a carbonate formation. It's a big volume of rocks with actually low permeability, because the permeability is related to the fracturation, and with the depth, the fracturation is decreasing and the permeability also. So yes, it's low. It's a medium agent, so it's not, we don't have the idea of how it could be mixed by different generation of fluid could be mixed. But yes, we have a problem with the understanding this very big aquifers inside big volumes of crystalline rocks. So I think that more study could be a good idea for the understanding of all this aquifer and the issue for the drinking water or other.
Yeah, we have another from Malbis. Thank you much. It says, thanks, Audrey, for the presentation. Is it possible to mention the name of the software you've used for the heat and flow lines modeling? Is it a
Yes.
commercial tool? Is it a commercial tool or in-house academic tool?
No, it's the COMSOL multi-physic tool, so software. So I have write it on the methodology. The name is at the beginning. Please wait. So COMSOL, C-O-M-S-O-L, multi-physic. Here you have the name. And it's
Okay.
a commercial software.
Commercial software, right. And I have another question for you, please. I came to one of those webinars, we call it Geoforos, the Forum for Geologists. And it was related to the age of the water. And the speaker told us that he was using hydrogen and helium to determine if the water is moving and how fast it moves. Do you have any analogs, or do you have the use of any of those elements, hydrogen or helium, in the water that may determine you how fast it moves? If it's a water which has been remaining a long time? May you use these two elements?
We didn't use helium. What we did during this study, you have the reference of the article at the end. What we did is lithium with actually the idea to see the signature of lithium inside these hydrothermal systems. But we didn't make helium measurement for this study.
Okay, thank you
I'm
very much.
Impressed of, yes, the geochemical study is on this article in Geochemistry, Geophysics and Geosystem. But I'm very interested by this methodology of helium you are speaking about, so please contact with me to say more about it.
I'll let you know, because it's been published. Sorry, but this in Spanish. Anyway, I may try to translate you or give you some clues related to that, because I thought it would be quite important to you to may use those techniques. And well, that's all, ladies and gentlemen. Thank you, Audrey. Thank you, Gonzalo, and our institution. So we'll see you then on the 21st of October, the same time. As also remind you that we'll be having a short course in geothermal projects, which will be presented by Mademoiselle Audrey Taillefer and our colleague Gonzalo Ruiz-Cebrián. Okay, thank you all for your...
Thank you very much, Carlos. Very much, Audrey. I will try to make try the same level as you make today.
You will, I'm sure.
It was super. So next week I will try to talk about analysis of images of logs with related to fractures and many other features, but I think the level that make Audrey is outstanding. So thank you very much, Audrey, and thank you very much, Carlos.
Gracias, Carlos. Gracias, Gonzalo.
Thank you all. We'll see you on the 21st. So that session's finished. So you may remain if you wish, whatever wants.
See you next week.
Bye.
See you next week. Bye, Audrey.